Okay. All right. So I stayed up until about 3 or 4 trying to render the video for lecture 6. At that point, I decided, well, we needed to run back through it with you guys anyways for lecture 7, so let's just go ahead and record it with you guys here in the classroom. So, lecture 7, ideal and conceptual measurements. This is actually going to be very short today because we're just focusing on ideal measurements. Lecture 6 notes are posted, as well as the, if you have any questions, feel free to post them to the YouTube page. So what we're going to cover today are just the ideal observations, specifically ideal range and ideal range rate. And we'll talk a little bit about simulating observations, and then next lecture, lecture 8, which will get recorded later today, we'll focus on conceptual measurement systems and talk more in depth about range and range rate and what they actually mean as opposed to the ideal measurement. So ideal range is geometric range. In other words, the instantaneous difference between the position vectors of the instrument and the satellite at some point in time. So propagation and other errors are because obviously range, even let's say, I have a laser rangefinder, right? The laser rangefinder still has some time of flight or some, the speed of light times 2 in order to hit the target and come back, right? We're not considering that in ideal range. We're just saying this is the instantaneous, the moment that the difference between the position vectors, my instrument, and where my satellite is, that's my range. And I know it instantaneously. And what we do is capture that propagation and other sources of error in our error term. So we see a difference between the ideal range, right, or the instantaneous range, and the actual observed range. And so we say, okay, that time of flight and all that, well, that's just, the ideal range plus some error. And that'll be our observed range, what we actually see. Geometric range is invariant between different frames because it's literally the difference in magnitude between the two vectors. So if we took it in the Earth-centered fixed frames, which is the one on the bottom because lowercase, it's not inertial, it's literally the magnitude of difference between the two position vectors, right? Whether it doesn't matter which coordinate frame it's in, it's still going to be the same difference. Range rate. So we differentiate the range with respect to time in order to find the ideal range rate. The range rate is literally the relative velocity along the direction of the range. So in other words, in some sense, how is my range changing, right? You'll actually find that when the range is at a maximum or a minimum, that the range rate is 0, right? Because it's changing direction at that point, right? So it's just our component of relativity to velocity between the observing instrument and the satellite and along the line of sight, which in this case is our range vector, our range vector. And so then finally, azimuth and elevation. So remember, in this case, we're talking about a topocentric system, most likely, because we have some ground station or the instrument is defined in some topocentric frame. And so we're going to port back our observations through elevation and azimuth as well. And so, assuming that it's defined as a topocentric system, we've defined our elevation and azimuth with those equations. So, we're actually nearly done with this lecture. Yes. Yeah. Because we're talking about ideal observations. And then we're going to go through the conceptual measurements, and we're going to hit the simulated observations pretty hard. But we'll talk about simulated observations real quick. So, going back a slide, we have our observed range and some instantaneous range. And so we're kind of starting to capture that there's a difference between the actual observed as part and the computed, right? So a computed range is, if I took, remember in your examples for chapter 2, you went through and you said, okay, first it's a 2-body, right? and I'm going to propagate forward in time 3,000 seconds for this space shuttle and determine what the subsatellite point is and all these other things, right? Okay. And then you did it with J2 perturbations, right? You added in the J2 perturbations to your propagation, and you added the J2 perturbation to your accelerations, and then you propagated forward in time, right, to 3,000 seconds. And they were different, right, because we had some perturbed acceleration. So one way we can think of that is that both of those are computing some range, because if I were to look at a ground station at that time, and I were to calculate what my range should be, that I've computed what it should be, right? Okay, well, then I'm going to observe the actual range at that point in time. Now, the difference between my observed and my computed is going to provide me a residual. And as you'll find out as we're going along further, a lot of what we do is going to be trying to reduce that residual or reduce the variance, essentially, right, that is obtained from the residuals. So we'll get some difference between the observed and computed, and we're going to try and minimize that difference or minimize that residual, either through linear regression, least squares, or what have you. And so I wanted to move back to this slide real quick because we can actually kind of think about it in terms of if I were to take my observed range minus my instantaneous range, because the instantaneous in some ways is actually computed, right? Because if we have perfect knowledge of our position on our instrument. And how did we have perfect knowledge? Well, we probably made some propagation and numerically integrated and said, yep, this is what it's going to be, right? Well, and so you would just take your observed minus your computed, and then you'd end up with some residual, right? Error or difference between the two, literally. So that's it for lecture 7. And then we'll move on how to actually simulate those. And we'll talk a little, we're going to use the examples from chapter 2, space shuttle example, and we'll show the observed minus the computed, and I'll probably have some graphs for you. And then we'll talk about the conceptual measurements. So time of flight, propagation, and get a little more in depth with range and range rate. And then we'll cover some typical systems, and then finally we'll end it with, we'll end it with difference measurements, and moving on to chapter 4, which is fundamentals of orbit determination. So, yeah, that's it for today. If you have any questions, post on the YouTube page. Glad to finally be back in the classroom and lecturing through. So.